All right, guys, so we're going to work on what's called optimization. So optimization, and there's many different ways they can do this. So when they talk about optimization, they're either optimizing a maximum or they're optimizing a minimum. So we're going to deal with maximums and minimums. So therefore, what we're dealing with is our first derivative. So we're kind of keeping in line with the first derivative and the second derivative test. So on this, you have I think on 66, you may have 4 or 5 of these, and then the rest of the problems are review. So if we're looking at this, you've got two numbers whose sum is 20, and you want to find, I believe, hold on, let me look. I grabbed this one out of a different book. You want the product as large as possible. So let's just let's take each one separately. So we've got to, we need to draw here. Let's go ahead and look, and we'll change this one to yellow. So we have two numbers. We have two numbers, x and y. So let's say xy equals first number, y equals the second number. Correct? And so that means their sum, we're adding them together, we got equals, so x plus y equals 20. All right, so that's our basic setup right there. Now, the product, we need the product as large as possible. So in other words, we want to know if x times y is its maximum, right? Is the largest. So the idea largest means that we're going to deal with a maximum. So we need to figure out how this is going to become an equation we're going to work with, because right now it doesn't work with anything. So if we look at this, so right now we have an equation of xy, but if we look up here and I solve for y, I get y equals 20 minus x. Isn't y also equal to 20 minus x? Well, if y is equal to 20 minus x, then that means f of x is equal to x times 20 minus x. So then f of x is equal to negative x squared plus 20x. And I want to deal with a maximum, so I just need the first derivative. The first derivative of x is equal to negative 2x plus 20. So I just took the derivative of my equation. This came from using the first pieces of information. Now I just know where is it a maximum? Where it's going to be where it's equal to 0. So I've got 0 is equal to negative, that's a negative 2x plus 20. So if I move the 2x over, 2x equals 20, x equals 10. So I know my first number is equal to 10. And then my second number is going to be equal to 20 minus 10. So that's also equal to 10. So I have x equal to 10 and y is equal to 20 minus x, which is also, that's a 10, is 10. So their largest product is 100. And so that's kind of what you guys will be doing. This is what we call optimization. We're optimizing the derivative to find either a maximum or a minimum. So they mess around with things, and so they do stuff like, let's do this one here. A farmer has, let's do 300 feet. 300 feet of fencing. He's going to create an animal pen. Pen next next, not nest, next to a lake, using the lake as one side, what is the maximum area and sides he can use? So these get a little different. So let's just look at the fact that he's got this fence. We know he's got a fence, and it's going to look like this, right? And that's going to have 300 feet on it. Now, what he's doing is he's building this on the side of a lake like that, okay? So he doesn't really need the blue line stuff. So if we take this and we look at it in a different way, we know that the perimeter is going to be x plus x plus y, because that's this right here. And that red line has got to equal 300 feet because he's got a maximum of 300 feet. So if we look at this, we have 2x for the two sides plus y is equal to 300 feet. Now, what I do know is that if I solve for y, I get y is equal to 300 minus 2x. The reason I do that is I want things in terms of one variable, so like x or y. You could have solved for y, it doesn't matter. So now if I look at this, okay, I got y. I know that y is equal to 300 minus 2x, and they change it, and they say, okay, now that we've used the perimeter a little bit, let's go ahead and talk about the area. We want to maximize the area, so the area has to equal a y times an x. So my y is 300 minus 2x times x, because it's just length times width, right? Length times width. Well, that's going to give me 300x minus 2x squared. How do I find the maximum area of that? Whoops. I find the maximum area by setting the derivative. So I'm going to set the derivative of 0. So we're going to take the derivative of this. So this is my f of x. So now I'm going to do my f prime. My f prime is 300 equals 4x. So x, negative 4x is equal to negative 300. I divide both sides by negative 4, and I get x is equal to 75. So now I've got a side of 75 and a side of 75. All right, so now we need to know what y equals. Whoops, come on now. Work with me. There we go. Let's do this color right there. So we need to know what y equals. Well, we know that y equals 300 minus 2x. So therefore, y is equal to 300 minus 2 times 75, which y is equal to 150. So now I know that y equals 150. So what's my maximum area? What is the maximum area? Well, the maximum area is going to be area of the maximum is equal to 150 times 75. And that becomes a pretty large number. So, I don't know. Let me slide over here and use the calculator. 150 times 75 equals maximum area is 11,250 units squared, because I didn't tell you. Did I tell you what kind of units? Nope, is feet. Sorry. So that would be feet, whatever. I didn't see the units. So it'd be feet squared. So he would have a side of 75. This would be a side. He'd have a side of 150. And then he would have a maximum area of 11,250 feet. So that's how we're dealing with optimization. The key, if you guys notice, the key is the setup. Make sure we're setting up and we're looking to get in terms of one variable. And that is what we call optimization. All right, guys, good luck, and I'll see you soon.